So welcome everyone to the panel discussion, Surviving the Anthropocene, Future Steps for the Three E's under Planetary Issues. So just so you know, this panel is being live transmitted, live streamed for those who are watching us from home via Zoom, and it's also being recorded. Wait just a second. I just want to make sure I have everything working. Wonderful. So before I actually introduce our panelists, I just wanted to tell us what the panel is actually about. And I'm going to read this out loud. Starting with the Industrial Revolution in the 18th century, the Anthropocene is our current geological epoch. Marked by unprecedented human-made global disruption, the Anthropocene presents existential threats that might have never been encountered before. Global warming, biodiversity loss, rising sea levels, and climate change-induced human displacement are just some of the many challenges we will continue to face. Guidelines for a sustainable future have been repeatedly proposed, and the planetary boundaries for our safe existence have been already established, which we're going to visit during the panel. Yet, more than 80% of the current global energy consumption still relies on unsustainable fossil fuels. And the COP27, which happened last year, if I'm not wrong, the COP27 negotiations have not delivered. To make things worse, the demand for oil and gas is expected to peak in the next 2 decades. Amidst this uncertain and tumultuous background, what are the future steps for ecology, ethology, and evolution? How can biologists contribute to the future of their disciplines while implementing best practices that guarantee the long-term survival of our planet? So these are just some of the questions that will guide our panel discussion titled Surviving the Anthropocene, Future Steps for the Three E's under Pressing Planetary Issues. So now I would like to introduce our panelists. So today with us, we have Dr. Eric Duzanga, who is currently based here at Western. So all our panelists are based at Western. Dr. Eric conducted his bachelor's in science at the University of Rwanda from 2006 to 2010, and his master's in science at the University of Gothenburg in Sweden between 2012 and 2015. The research projects for both bachelor's and master's theses focused on tropical tree physiology and were both done within the University of Rwanda and the University of Gothenburg collaboration. He defended his PhD thesis on boreal climate change ecophysiology at the University of Western Ontario here with us in 2019. After having worked on a couple of postdoc projects in Sweden and the UK, he is now a postdoctoral associate in the Center for Climate Change, Sustainable Livelihoods, and Health at the Western University. So Eric's main research interests are to understand and predict how tropical and boreal trees will respond to climate change. Our next panelist, Dr. Katrina Moser. Dr. Katrina Moser is a paleolimnologist and climate scientist. The majority of her research is focused on showing how climates have changed over thousands of years and reporting on the response of lake ecosystems to these changes. This knowledge provides a context for the profound changes underway today and helps us to plan the future. Her research has mainly been in remote alpine and northern regions where anthropogenic climate change is occurring most rapidly, but it is also ongoing here in southwestern Ontario. In her 30 years of research, she has observed dramatic changes in lake ecosystems and have become increasingly frustrated by the lack of action being taken to address this climate change. So I'm really happy you're here with us today, Dr. Katrina. To help remedy this situation, she put together a team to co-develop a course called Connecting for Climate Change Action that braids together Euro-Western science and indigenous knowledge to inspire students to take action to address climate change and make the right choice for a better future. Last but not least, we have Dr. Hugh Henry from our Department of Biology here at Western. So Dr. Hugh is a terrestrial plant ecology with interests in biogeochemistry, community ecology, physiological plant ecology, and global change ecology. He uses field experimentation, laboratory methods, and theoretical modeling to explore questions ranging from resource acquisition by individual plants to species responses at the community level and nutrient cycling at the ecosystem level. He is particularly interested in exploring how plants and microorganisms interact to regulate nutrient cycling in natural systems. Thank you so much for being here with us today. I'm very excited to moderate this panel. So let me quick observation, quick note about the panel. So, well, I'm not a climate scientist, although I'm very interested in the climate crisis. But to come up with the questions and topics of this panel, I have based myself in materials found online. Just like, for instance, the Guardian has a beautiful series of investigations about climate action really matters. The Living Planet report, which was published last year by WWF, and also this beautiful book by Greta Thunberg, the Climate Book, which I highly recommend. So the panel touches upon topics that are covered in those materials as well in these materials as well. So we have topics from published work, topics from Our World in Data as well, which is a beautiful website I highly recommend. And I use some visuals from The Visual Capitalist, which is also a great source online. And here is our structure for the day. And again, this structure is not set on stone. I think we can, be flexible and adapt. And we may not cover all topics, but let's try to cover all of those. So for the first part of the panel, the first hour of the panel, we will learn what the Anthropocene is and learn how we can, so what a healthy planet looks like. So we're going to learn about the 90 planetary boundaries, what are the climate tipping points, and what is the Living Planet Index, which I think really is perhaps the closest concept to us biologists. And then we have a short break. Depending on how long we take in the first hour, we can have a break of 10 minutes or so. And then we're going to discuss carbon bombs, which have been revealed by The Guardian, and how, I think it's important to end discussions like this perhaps in a promising note, if you will. So we're going to talk about carbon removal and promising technologies. But let's just jump right in. And I have my notes here. Yes? So, as we can see here, the Anthropocene, as I mentioned earlier today, really is our current geological epoch. However, the problem is there is some controversy around whether Anthropocene exists, whether Anthropocene is a thing. And I would like to hear from the panelists what they think of this, whether the Anthropocene is a real thing, whether there is consensus on the existence of this geological epoch. And what I'm showing you here is a process called the Great Acceleration. So the Great Acceleration is the dramatic and continuous and roughly simultaneous surge across a large range of measures of human activity, first recorded in the mid-20th century and continuing to this day. And usually those measurements, they can be classified in two main categories. We have the measurements on socioeconomic trends, which I'm showing you right now. For instance, we have this surge in fertilizer consumption, urban population as a whole, GDP, and so on. And I'm showing you here just the very tip of the iceberg. We have 9 graphs or so that represent this surge. But we also have Earth system trends, which are also, they follow the same pattern, right? We have an increase, which again, that's not a surprise for us, this surge in carbon dioxide in our atmosphere, nitrous oxide, methane, and other gases and other materials as well. So my question to the panel is the Anthropocene a real thing? And whoever feels free to start.
So I'm trying to decide. This is like a loaded question to me, and I'm trying to decide how I want to start. I think I'm going to first tell you a tiny bit more about myself so you know where I'm coming from in answering this question. So my training started as a geologist. My plan was to be an exploration geologist. And maybe in year 3, I realized that wasn't quite the direction I wanted to go. And I was much more interested in the environment. So my master's thesis and PhD are in geography. I did get some training in a biology department at Queen's with John Small as well. So that's kind of my background. And Matthias mentioned that I've been working on this course, Connecting for Climate Change Action, where I've been working with Indigenous scholars. And I have to say that's really shifted my perspective and thinking about climate change and about humans' place in Earth systems. So thinking about the Anthropocene, and again, this is kind of a loaded question, I want to start just giving a tiny bit of history. So Eugene Stormer is the person who is credited with first using the term recently. There's actually roots that go farther back in time, but around the 1980s, he was an ecologist and a limnologist, and he and another fellow, Paul Crutzen, have published quite a lot now about the Anthropocene, and really, I think their goal was to bring attention to the fact that humans are having a huge impact on our systems. So I think that's the value of that term. It's really brought attention to something that's very, very important. But the controversy that Matthias alluded to is around the name and around the timing. And the name, I think there are weaknesses in the name because it suggests that all humans are equally responsible for the changes that we're seeing to Earth systems. And that's not quite true. If we look, for example, at climate change, 23 of our rich developing countries are responsible for at least half of the emissions, and the other 150 countries are responsible for the other half. So that suggests, right, that the responsibility is not equally shared. We can also look at companies, right? So there's 20 companies responsible for about 70% of fossil fuel emissions. So again, it's not evenly spread across all of our population. And so that is one issue. Another issue around the name is it sometimes suggests that humans are separate from Earth systems, and we're not. We're intricately tied to Earth systems. We're part of the biosphere. And you know, I love a quote that I heard from an Indigenous scholar, Wasakim Nin. The Earth doesn't belong to us, we belong to the Earth. And I think when you change your perspective and start thinking about it a little bit differently, even as a scientist, it really shifts how you think about moving forward around issues related to what we'll call the Anthropocene for now. The other issue is the timing. When does the Anthropocene start? And this is really controversial. People have suggested it could have been at the onset of agriculture. We know that the onset of agriculture led to increased greenhouse gases. Some people have suggested it's the start of the Industrial Revolution. That's what Eugene Stormer wrote about. Some people have suggested it's a bit later, even a bit earlier, related to colonialism. And the IPCC, in their latest report, for the first time links climate change specifically to colonialism. And I think that's really important. And again, getting at this idea, we're not all equally responsible, and we won't all feel the effects the same way. And then, again, you alluded to in your slides, just like when we name a new species, when we name a new epoch, there's a whole series of rules around that. And so geologists, stratigraphic scientists have worked on trying to find a layer, something in the rock record that defines the Anthropocene. It has to be something that persists for thousands, millions of years. And the best thing they can find is radionuclides that increase as a result of bomb testing. That's 1950 roughly. But is that really the start of the Anthropocene? Well, if you're a geologist and you're thinking on timescales of millions of years, 1850, 1950, what's the difference, right? But if you're today and you're doing policy decisions, 1850, 1950 makes a big difference. So these are some of the issues around the Anthropocene that I think are really important to think about sort of as we go forward. And I'm sure I've taken more than my fair share of time, so I'll let someone else talk.
Okay, yeah, thank you very much. I think what Katrina has said, I can only add that. So the idea about regarding Anthropocene is basically trying to show how human activities have had a tremendous impact on our Earth system. And to me, one way I look at it is it's true. So basically based on the data we get from scientific papers and also on some of these graphs that were showed here, how CO2 has been increasing over time, and the spike in increase in CO2 is significantly related to industrialization and fossil fuel burning, which is basically the major mean of our socioeconomic development. And I can partly say that from basically reading the literature, and also when I started to do research, like back in 2009, so I studied specifically, for example, how carbon fixation in plant changes when plants are grown in different environment. And one way, or the instrument we use, we usually set the ambient CO2 condition of plants before we change other parameters. And this value, when I started, was around 400. And now over time, when I go to do my research, my measurements, I'm studying the same thing. I have to think, oh, which ambient CO2 should I put in my instrument? And now it's around 415. So yeah, I can say that it's true that humans are having a significant effect on our environment. And
yeah, I don't have much to add in terms of defining the Anthropocene, but this idea of the great acceleration and the shape of all those graphs that were up on there. And I guess what I guess is maybe disturbing, or you can see it as a challenge, is, we talk about moving from a economy of growth to one of sustainability, but what concerns me about those figures is more when it comes to demographics in the coming years. We have to transition from that rapid growth to something else. And when we think in terms of, let's say, population, which is current projections is stabilized, let's say, at 10 billion, but we already know the problems of the demographics when the birth rate goes down and the pressures it puts on societies. And my concern about that in the context of our efforts towards fighting global change problems is if we have, let's say, older population, smaller tax base, people's priorities change. You look at now a lot of the stresses in society, what concerns people, and if people essentially feel they have less out of life, I'm concerned that it'll take away from concerns about the climate, and people will be more focused on their immediate needs, simply because of that pressure of the demographic pressure put on society. So I know, I think a challenge for, I'm not an economist or anything, but the challenge is to think of how to have a sustainable society. But I think the transition from that to sustainable is an awkward time in terms of pressures on society, and then how it translates into the effort we put into to protecting climate, the globe.
Okay, I'm connected again. Wonderful. Thank you very much. I must say, I had no doubt the panel was going to be a success, and I can already feel it. We had really put together the right lineup. Thank you very much for your input on this question.
Does anyone ever talk about the great deceleration?
I have not seen, but I mean, I guess this is where we need to head towards, too, right? But I haven't seen the great deceleration yet. Anyway, so moving to the next topic, as I said, the purpose really is to be an informational session, so we are all learning on the go together, including myself. So what I would like to talk next really is the 9 planetary boundaries. And I have a few notes in here that I would like to share with you. The planetary boundaries concept presents a set of 9 planetary boundaries within which humanity can continue to develop and thrive for generations to come, which speaks to what Hugh just mentioned in terms of how we can balance out our continual growth with Earth. In 2009, former Center Director Johan Rockström, and I'm butchering names here, I apologize, led a group of 28 internationally renowned scientists to identify the 9 processes that regulate the stability and resilience of the Earth system. The scientists proposed quantitative planetary boundaries within which humanity can continue to develop and thrive for generations to come. Crossing these boundaries increases the risk of generating large-scale, abrupt, or irreversible environmental changes. And again, the focus really is from me, but I would say abrupt and irreversible changes. The focus comes from me here. Since then, the planetary boundaries framework has generated enormous interest within science, policy, and practice. So what we are seeing here in the slide right now really is a diagram from these authors showing us the 9 planetary boundaries. And as we can see, each boundary really is highlighted with different colors and at different levels, indicating that those in which, the boundaries in which we are within the green area, we haven't really surpassed a critical point yet, but there are boundaries in which we have already extrapolated, and perhaps it might be a little too late, to mitigate the cascading effects of our anthropogenic factors. But you know, there are 9 planetary boundaries, so this can be a little overwhelming. And my question then to the experts is there a planetary boundary that is the most important? And I say between quotes, the most important, because we know Earth is all, those systems are all interconnected. So chances are we don't have just one, the most important. But let's find out together. And which boundary are biologists ready to study? Because let's remember, this panel, the audience here is for biologists. And I would like us to carry on with our discussions with biologists in mind, right? So which of those boundaries are biologists best equipped to study and then inform policy changes in that direction?
Okay, I can maybe start. As Matteo said, I think all these planetary boundaries, there is not one you can say easily that is more important than the other one, because they are all interconnected. So, for example, if you look at the land system change, so this will include things like deforestation, basically habitat loss, and this would feed back again to the climate crisis, right? Which is in itself is another boundary. Yeah, and also changes in biogeochemical cycles as well are affected by land use change, and they can also feed back to the climate and the climate change crisis. So yeah, to answer that question, I would say that yeah, they are all interconnected, and there is not one you can single out as like standing out as the most important one.
Well, I can start by saying, as someone who studies that biogeochemical cycle of nitrogen, I'm very impressed by this figure and validating my work. But but actually, that does touch on a point that I agree with what Eric was saying for sure. And I think the way we conduct science needs to really be much more towards this approach of essentially integrating across and taking like a sensitivity analysis, saying what matters most. And I think that's sort of at odds with what we currently do, which is, each of you has your own project. I have my own project. We study something. And, when I get a set of results, the first thing I do is I try to tell a good story. I want to maximize its impact. I want to sell it for the most that I can sell it for. And because it's not going to benefit me to downplay the results or to put it in the context of things that matter a lot more. So I think there's sort of a healthy idea about competition in science. There's limited resources. You want people to make a good justification for the work they're doing. But on the back end, I don't think we do enough to put everything together in the larger context, each of us has unfortunately become put in the role of being a salesperson and to just promote what we do. And really, we should be able to look at our results and say, well, I'm glad to report that we can now cross this off as not being so important. And we can focus on these other things. And yeah, so I think the way we conduct science often doesn't lend itself towards this approach where we try to identify the key sensitivities in what we're doing. So I don't know moving forward how to solve that problem, but I have that's become sort of a thing in my mind in recent years that, and you know, I think one of the great things about an ecology conference, I think ecologists give really good talks, very compelling talks, but we've all been trained to almost be like an infomercial at times and to really oversell what we're doing. And it doesn't help move forward with this idea of what should we focus on.
Yeah, I don't have too much to add, but I would pick up on what Eric mentioned about all of these boundaries are so integrated. So how do you pick one? I think it's nearly impossible. And I think the other thing that I worry a little bit with a diagram like this is how do you define the threshold? And I think you want to be careful there because those thresholds we've seen, for example, with contaminants can shift over time, right? So I don't think you want to focus on one at the expense of others. I think, well, the other thing to be really mindful of is you might tackle one and it might have surprising effects on another. So I think you really have to look at it holistically and all of these things together. I did want to pick up on something that Hugh mentioned too about competition and also your comments from the last question about demographics and growth. And to me, one of the problems I think we have in society is this focus on growth and this focus on competition and being the best. And I really think to tackle climate change, we've been kind of going down the same road now for 30 years, and we really haven't made very much progress, to be honest. I don't want to be negative, but that's the truth. If you look at where we are with carbon emissions, we're really not doing a great job. So I think we have to start thinking about things in a completely different way. And I agree, that's not going to be easy, but in the end could be really a positive step forward. So that's one of the, I guess, things I'll pick up from those comments, but I'll stop there.
To return. So what goes hand in hand with what we just discussed really is the climate tipping points, which, by the way, were also proposed by the same center that came up with the 9 planetary boundaries. And for us to understand what climate tipping points really are, I will read a short excerpt from a paper that was published last year in Science by David Armstrong, again, from the same Stockholm Resilience Center that proposed the 9 planetary boundaries. Climate tipping points are conditions beyond which changes in a part of the climate system become self-perpetuating. So that really is the idea of a tipping point. Once you reach it, there's no way back. These changes may lead to abrupt, irreversible, and dangerous impacts with serious implications for humanity. And I must say, so there are 2 types, and I'm not sure, next slide. There are 2 types of climate tipping points that can be categorized. So we have climate tipping points called regional tipping points, in which once we reach this threshold, there will be environmental impacts at the regional level. But you also have core climate tipping points, in which once we reach those tipping points, there will be a cascading effect in the planetary scale. And currently there are around 9 core tipping points and 7 regional tipping points. This graph doesn't break down the categories, but what this graph shows us really is which tipping points we have already, to a certain extent, reached, given our current temperature increase estimates. Let's remember, with the Paris Agreement signed a few years ago now, we were hoping to keep the increase in temperature below 1.5. And if we carry on with business as usual, we will not be able to keep this temperature increase below 1.5 degrees Celsius. This is also important to keep in mind. So as of now, if we reach any temperature increase of 2 degrees Celsius, we will have extrapolated several climate tipping points. But as you can see, there are some tipping points in which we have a wiggle room, right? So again, I think that all these concepts go hand in hand with what the panel just discussed. But my question for the panel really is, what can we do about the tipping points that have been reached already? And I'll return to the previous slide just to show us that we are talking about those in here, right? So what can we do about those tipping points, and which tipping points should or could biologists focus on?
Yeah, so one quick thing I'll mention is it's not really of direct interest to ecologists, is that I'm most concerned by the tipping points that cause further extreme human behavior. So anything that puts pressures on countries, let's say to launch a nuclear weapon or something, becomes an even bigger ecological thing. So in the back of my mind, I'm concerned about anything that feeds back on human behavior in a more extreme fashion. But if we bring it back to what do biologists do? Yeah, I think my previous comment was kind of, I guess, in essence, one of pay less attention to p-values and more to effect sizes. For this, I would say, when we read the literature and design our own experiments, to think a lot about treatment levels, and because that's what this is really coming down to is how we're interpreting. So when you go through the literature, you tend to say, well, what was done in the experiment and what was the result? You might say, well, they applied warming or they added nitrogen. And as someone who works on nitrogen cycling studies, we're concerned a lot about atmospheric nitrogen deposition. So this is nitrogen pollution from the atmosphere. And people study that by dumping nitrogen onto plots. And they tend to add around 10 times more than what is seen in most systems. Why do they do that? Part of it's just precedent, but they're testing the limits of the system, and they're showing a strong effect. But you have to be very careful in interpreting those results. So I think I've, as a reviewer, been presented with a lot of papers trying to compare one aspect of global change to another. And it's amazing, on one hand, how often people stack the deck. One study I saw was trying to explain why millipedes were the most important part of global warming. And they basically warmed up mesocosms by 2 degrees, and then they had the presence and absence of millipedes. And of course, the presence of millipedes had much more of an effect than 2 degrees of warming. So they said, well, if warming affects millipedes, the millipedes are going to be the key factor here. And so what I'm getting at here is you have to say, well, is 2 degrees of warming enough? They probably should have done 3 or 4, and they probably shouldn't have gone from 0 millipedes to 100. So I guess the other part of that would just be, it's nice if you can have a response curve as opposed to control and treatment. And so I think one of the most important things in scrutinizing our own work and the work we read is to think about treatment levels. And it doesn't answer your question directly, but it does sort of put a sense on, I like this way of thinking, because I think that's what's going to get us forward, is to think about those thresholds and to actually connect it to our experiments.
Yeah, thank you. Yeah, so one comment I can make about this threshold, what to do about the threshold you have already reached. So for me, maybe I can just give a simple example about my research that we are doing in the tropics, where we are looking at, so basically most of the literature coming on impact of climate change on forests come from the Amazon, and it's clearly showing that the trees are dying. And one project we are currently involved in Rwanda, we are looking at what factors are driving trees to die under warmer and drier conditions. So basically, what are the traits exposing some trees to die, and what can we do about the forest in the tropics? So one thing we are doing is to basically partly touching on comments of you, like exposing them to different climate conditions, but having a control, but then having others being exposed to a significantly larger, warmer, and sometimes unrealistic warming treatment, and look at which species are dying and what are the consequences of the species that are dying, and what can they inform on the reforestation program. And one thing we are working in this project is to basically study those natural, the tree species growing from natural forest, and from there look at which species are dying, which ones are surviving in a warmer and drier environment, so that we can kind of restore forest, but using the trees that are likely to survive in those future climates. So yeah, so one way is to basically look at research to see the impact of climate warming on some species, and then from that knowledge look at what we can do to restore those degraded ecosystems.
So Hughes talked about how we should do science to tackle these tipping points. And Eric's given a really nice example of a project that you could, or research that you can do to contribute to understanding, how ecosystems help reduce carbon in the atmosphere. My answer is going to be super simple. All of these things are related to climate change. So if we want to contribute to this, we have to mitigate carbon emissions. We have to reduce carbon emissions, whether it's we reduce burning fossil fuels, or as ecologists, as biologists, you have a huge way to contribute to mitigation in thinking about how do we reduce carbon in the atmosphere through ecosystems, through photosynthesis, right? So I think that's combining these 3 points kind of points a direction for biologists to contribute to mitigating climate change.
Oh, I am turning off my mic just so we don't have interference. That's why we have, and we need to wait a few seconds. Thanks again. This was great. So moving on, probably we're going to move to the topic that is the closest to our audience here. What I'm showing you here is the Living Planet Index, which was actually published last year by WWF with the Living Planet report. And what we can see here really is, and I'll read from our World in Data website. The Living Planet Index is the biodiversity metric that always claims the headlines. So the Living Planet Index reports an average decline of 69% across tens of thousands of wildlife populations since 1970. And this is what the graph behind me is showing right now. However, this does not tell us anything about the number of individuals, species, or populations lost, or even the share populations that are shrinking. The Living Planet Index measures the average change in the number of individuals across the world's animal populations. And let's just take a moment to let that sink in. So we're talking about animal populations. So even though, I don't think I need to convince anybody here in this room that other forms of lives are just as important. Let's remember, we live in a planet that is dominated by the microbial world, right? So we live in a planet of bacteria and viruses in the sheer number of species and also in biomass. But still, we tend to study more what we can see with our naked eye. So the Living Planet Index really takes into account only animals visible to the naked eye. Moving on. So a population is defined as a species within a geographic area for the Living Planet Index. So despite being the same species, we can have different measures, different numbers. And I'm going to show you in a second what this means. So here I'm showing you a real example of 2 populations of rhinos, one in Tanzania, one in Botswana. And these populations have been tracked since 1980. And these numbers have been used to inform the Living Planet Index. So as we can see, the population in Tanzania actually had a decrease of 96%. Meanwhile, the population in Botswana had an increase of 67%. So it is hard to come up with an index that really captures all the dynamics happening in all populations of a single species. So I just want us to have that in mind, right? Because, saying that the population worldwide the biodiversity worldwide has declined 69%, it is a catchy piece of news that, it's easy to throw into the headlines, but us as biologists, and, I would say data-driven scientists, it's important to have this in mind. Anyway, even though we did have an increase in the rhino population in Botswana, if we combine those numbers, we can see that overall there was a decrease of 95% of the population of black rhinos across the world. So with that in mind, with this drawback, I want to show you some of the breakdown of these numbers. And as we can see, so this map is divided again according to the Living Planet report published by WWF last year, and they divide the world in 5 major areas, geographic areas, which are combined not only given geographic parameters, but also biodiversity parameters. And as you can see, different areas of the planet have different decreases. Perhaps not surprisingly, in Latin America and the Caribbean region, experienced the largest decrease of 94%. And I must say, Bolsonaro must have contributed to that a lot. I'm from Brazil, so I can talk about Brazilian politics. Thankfully, he's no longer in power, thankfully. But still, we are seeing a decrease across the globe. And seeing a smaller decrease in North America does not mean that North America is off the hook. To the contrary, right? When I saw these numbers, I did wonder, do we have a slower decrease in North America because we started off with already a lower biodiversity? So that's something to ponder about. But enough of me talking, I'm not a specialist. I would then go back to the panel and ask, what can biologists do about our current biodiversity crisis? Because really, there is no doubt we are experiencing right now a biodiversity crisis.
Okay, I can briefly comment on this question. I think one important aspect of biologists in this biodiversity crisis is to, first of all, document all the known species, because there is a recent study I came across which was saying that some of the species are actually dying before we even discover them, especially in the Amazon. So one way biologists, especially conservation biologists, I think we need to first identify all the all the species, even those that are understudied, especially in these rich biodiverse ecosystems in the tropics. And also, as Matteo said, so perhaps the reason why we're not seeing a lot of changes for example, in the boreal systems, in high altitude forests, is because we already have a lower number of species. So for example, in the boreal forest, we have about 8 species, abundant 3 species. So we may not detect easily the changes in these forests, but for example, if you go in the tropics where there are thousands of species, then you definitely pick up these even small changes. So one way is to document all the species. And once we identify the species that are at greater risk, then develop conservation priorities for those species, and also come up with the restoration strategies to be able to reverse this degradation of ecosystems.
Yeah, I would say these figures also really highlight, to me, the distinction between global change and climate change, in the sense that land use, invasive species have already had huge effects, whereas climate change is sort of more of an emerging problem in terms of the effects that we're feeling. And it's really kind of interesting from my perspective. So I was at the OE3C, it was the OEEC conference in 1997 here at Western. So I've been thinking about global change, I guess, for since the turn of the century. And back then, like early 2000s, climate change was a future problem mostly. And the timing of things, if you're sort of comparing changes over time, was already projections for 2050. So everyone say, okay, we're gonna do an experiment, we're gonna compare now, which is the control, to 2050, which is the horrible future. And back then, it used to dawn on me that if I looked at my lifespan, I'd be like, yeah, I should probably live to around 2050 unless I have some sort of horrible accident before then. So I said, I guess as a scientist, I'll get to do these experiments, live to see what happened, and then die. But that sounds kind of morbid. But what's interesting to me now, now that it's we're hitting the halfway point to 2050 from 2000, we're now seeing climate change finally becoming something that is actually having some noticeably strong effects. So when we design our experiments, what is the control now? We're now at a point where we're no longer able to say, well, this was the pre-climate change effect and what's not. So, you were talking about, this game you play where you're making comparisons of changes and regions. And moving forward, it looks like the new era of climate change experiments looking at mechanism are going to have to take a different approach. And maybe we'll transition more to documenting the effects of climate change as opposed to always playing this game of trying to predict climate change. Because we're already, when my career started, it was always the future. Now it's the present in terms of the actual effects.
Yeah, I'll just add a quick comment. Sort of picking up on what he was saying and thinking a bit about the impacts of both climate change and some of these other issues that affect biodiversity, whether it's overhunting or loss of habitat. I think our populations of organisms right across the board, plants, animals, are all stressed by various human activities. So for example, I work on lakes. There's a paper just recently published saying oligotrophic lakes really don't exist anymore, right? There's nutrients going in all sorts of ways. So what happens when you add on top of that climate change? Or if you're thinking about a lake that's changing and you're not sure, is it climate change or is it nutrient inputs? What's driving these changes? If we think, for example, of Lake Erie and algae, and how do you tease those apart? How do you quantify the different impacts of these stressors? So I think that's really important in thinking about biodiversity and how do we protect biodiversity moving forward. I don't know. Did either?
Well, what I'm hearing is that biologists have a lot of work to do, which is a good thing, I would say. That means hopefully, our employability will just continue increasing. And I would say, I think right now is a good moment for us to have a quick break. And then we can, I would say 10, so right now it's 3:03 in my clock here. Let's take a 10-minute break and then we can resume until 4, okay? Thank you very much. Thank you.